Imagine standing in complete darkness, not the darkness of a power outage, not the darkness of a moonless night in the countryside, but a darkness so absolute, so total, that the concept of light itself has become nothing more than an ancient memory preserved in the fossils of dead physics. The sky above you, if you can still call it a sky, contains no stars. Not a single one. Every sun that ever burned, every beacon that ever guided a sailor home, every distant fire that ever made a philosopher look upward and wonder, all of it gone, extinguished, forever. This is not science fiction. This is not a myth or a metaphor. This is the guaranteed future of our universe, written into the laws of physics with an ink that nothing, not intelligence, not civilization, not the most advanced technology imaginable can erase. The last star will die. And when it does, it will mark the end of an era so vast that the entire history of humanity, from our first fire to our last breath, will represent less than a single frame in a film that runs for trillions of years. The question is not whether this will happen. The question is what it means for the universe, for the concept of life itself, and for the strange, fragile experiment called existence. To understand the death of the last star, you first need to understand what a star actually is. Most people think of stars as permanent fixtures, eternal lights pinned to the ceiling of the sky like decorations that have always been there and always will be. But stars are not permanent. They are not fixtures. They are processes. They are controlled explosions. They are enormous, ongoing nuclear reactions taking place across distances so vast that the human mind cannot honestly comprehend them without first abandoning its sense of scale. Our own sun, the star that makes all life on Earth possible, is a ball of gas roughly 1.4 million kilometers across. So large that approximately 1.3 million Earths could fit inside it. And yet, by cosmic standards, our sun is embarrassingly ordinary. There are stars in our galaxy alone that would swallow the orbit of Jupiter without breaking a sweat. A star is born when a cloud of gas and dust, mostly hydrogen, the simplest and most abundant element in the universe, collapses under its own gravity. As the cloud contracts, it heats up. The atoms begin moving faster and faster, colliding with increasing force, until eventually the pressure and temperature at the center becomes so extreme that something extraordinary happens. Hydrogen atoms begin to fuse together. Two hydrogen nuclei slam into each other with such violence that they merge, forming helium and releasing a tremendous burst of energy in the process. This is called nuclear fusion, and it is the engine that powers every star that has ever existed. That energy pushes outward against the crushing inward pull of gravity, and for a time, sometimes millions of years, sometimes billions, the two forces balances each other in a kind of cosmic standoff. The balance is what we call the living star. The energy released by this process is staggering beyond human intuition. Every single second, our sun converts approximately 600 million tons of hydrogen into helium through nuclear fusion. Every second. And in doing so, it releases energy equivalent to billions upon billions of nuclear bombs detonating simultaneously. That energy travels outward through space, eventually reaching our planet as the warmth on your face on a summer afternoon. It drives the wind and the ocean currents. It powers photosynthesis in every blade of grass and every leaf on every tree. Everything alive on Earth is, in the most literal sense possible, a byproduct of stellar nuclear fire occurring 150 million kilometers away. But here is the critical thing to understand. A star is consuming fuel. Hydrogen is not infinite. Even in something as enormous as a star, it is being burned, fused at a ferocious rate every moment, every day. And when the hydrogen runs out, the star's story begins to change in ways that are both violent and beautiful. What happens next depends almost entirely on how massive the star is. This is where the universe reveals its most dramatic storytelling instincts. A star, like our Sun, when it exhausts the hydrogen in its core, will begin to expand. The outer layers puff outwards as the internal balance shifts, and the Sun will eventually swell into what astronomers call a red giant, a bloated, cooling star that, in our Sun's case, will likely engulf Mercury and Venus and possibly even reach the orbit of Earth. For a few 100 million years, it will burn through helium in its core, fusing it into carbon and oxygen. And then, with no more fuel to sustain the reaction, the Sun will shed its outer layers in a slow, graceful exhalation called a planetary nebula. A glowing shell of gas drifting outwards into space, illuminated by the hot, dense remnant left behind. The remnant is called a white dwarf, and it is essentially the Sun's core, roughly the size of Earth, but containing most of the Sun's remaining mass, slowly radiating away the last of its heat over billions of years. More massive stars tells a more violent story. A star with many times the Sun's mass burns through its fuel faster and more furiously. The internal temperature gets hot enough to fuse heavier and heavier elements. Helium into carbon, carbon into oxygen, oxygen into silicon, silicon into iron. Iron is where the story ends. Iron cannot release energy through fusion. In fact, fusing iron requires energy rather than producing it. When an iron core builds up at the center of a massive star, the nuclear fire finally decisively goes out. And in a fraction of a second, literally less than a second, the entire core collapses under its own gravity. The outer layers, no longer supported, come crashing inward at a significant fraction of the speed of light, and then rebound outward in a catastrophic explosion called a supernova. For a brief period, a single exploding star can outshine an entire galaxy of hundreds of billions of stars. What remains is either a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons, or, if the star was massive enough, a black hole, where gravity has won so completely that not even light can escape. These are the fates of stars: birth, life, death. A cycle that has played out across the universe for nearly 14 billion years and will continue for trillions more. But it will not continue forever. And this is where our story turns towards its inevitable haunting conclusion. The universe had a beginning. Approximately 13.8 billion years ago, the Big Bang filled the cosmos with matter and energy, and within the first few 100 million years, the stars ignited. The universe was young and rich with hydrogen, and stars formed in enormous number clustered together in galaxies, lighting up the darkness in a cosmic celebration of nuclear fire. We live in that era right now. We are in the grand timeline of the universe, extraordinarily early. The universe is only 13.8 billion years old, and astronomers estimate it will last for timescales that make the number look like an infant's first breath. The era of stars, the Stelliferous era, a cosmologist named it, spans roughly from 100 million years after the Big Bang to about 100 trillion years from now. 100 trillion years. For context, that is more than 7,000 times longer than the current age of the universe. During this vast epoch, stars will continue to form from clouds of gas, burn for their allotted lifetimes, and die. But there is a catch, a critical universe-altering catch. The raw material for making stars, hydrogen, is not being replenished. With every new star that forms, some hydrogen is converted to helium and heavier elements. With every star that dies, that hydrogen is either locked up inside a dwarf star or a neutron star or a black hole, or it is scattered into space as processed enriched gas. Gas that is now partly helium, partly carbon, partly oxygen. The pristine star-forming hydrogen that flooded the early universe is slowly, inexorably being used up. The universe is running out of the one ingredient it needs to keep making stars. This has profound consequences for the timeline of cosmic history. The stars forming today are, statistically speaking, already leaning towards the smaller, dimmer end of the spectrum. The great, brilliant blue supergiants of the early universe, stars dozens of times more massive than the Sun, burning bright, hot, and fast, have largely already been born and died. The universe has already passed through its most spectacular phase of star formation. What remains in the long view is a slow winding down, a gradual dimming as stars form less frequently, burn more quietly, and die without replacement. The type of star most likely to be forming in the current and future universe is the red dwarf. Red dwarfs are the universe's most common and most conservative stellar citizens. They are small, sometimes only 1/10 the mass of the Sun, and they burn at temperatures so low that they glow a deep, dim red rather than the brilliant white or yellow of larger stars. They are extraordinarily frugal with their fuel. Whether a star like our Sun will live for roughly 10 billion years, a red dwarf with 1/10 the Sun's mass might burn steadily for 10 trillion years. Some of the smallest red dwarfs are estimated to have lifespans extending to 100 trillion years, longer than the entire projected Stelliferous era itself. These dim, patient, almost miserly stars are the last holdouts. They are the universe's final lights, and eventually even they will go out. The last star to ever burn in the universe will almost certainly be a red dwarf. It will be a small, dim object, barely qualifying as a star by any measure of grandeur. It will glow a faint, deep red, emitting just enough light and heat to maintain its nuclear reactions, consuming its fuel at such a glacial pace that millions of years pass with barely perceptible change. Around it, there may or may not be planets. Those planets, if they exist, will be bathed in a dim, rust-colored light that is nothing like the sunlit world we know. The sky above such a world, if any atmosphere remains, would be a perpetual twilight, the star appearing larger than our sun but far less bright, a sullen ember hanging in the heavens. And then, somewhere in the incomprehensibly distant future, roughly 100 trillion years from now, give or take, the last of the hydrogen in the core of that last red dwarf will be fused into helium. The nuclear reaction will slow. The outward pressure will weaken. Gravity, patient and relentless as ever, will begin to win. The star will contract, cooling further, dimming below the threshold of nuclear fusion. It will become a black dwarf, a cold, dark, dense remnant, indistinguishable from the background darkness of a universe in which the concept of starlight has become a relic of a forgotten past. There is a haunting detail that astronomers add to this picture. Black dwarfs, strictly speaking, do not yet exist anywhere in the universe. The universe is not old enough. Even the oldest white dwarfs, the remnants of the earliest stars to die, have not had sufficient time to cool completely into true black dwarfs. The cooling process takes so long that no black dwarf has yet formed in the nearly 14 billion years since the Big Bang. They are a future phenomenon, a class of object that belongs to a cosmic era so far ahead of us that the mind can only grasp it through abstraction. But they will exist, and the universe of the far future will be populated with them. Countless trillions of cold, dark stellar corpses floating silently through an ever-expanding, ever-cooling void. Now step back, much further, because the death of the last star is not actually the end of the story. It is only the end of the first chapter of the universe's long, slow decline. What comes after is a timeline so vast and so strange that it belongs to a domain of cosmology that feels more like science fiction than textbook physics. But it's real. It is the projected future of our universe, based on the best understanding of the laws of physics that humanity has ever achieved. After the last star dies, the universe enters a phase that cosmologists call the Degenerate Era. In this period, stretching from roughly 100 trillion years to 10 to the power of 37 years, an absurdly large number that requires scientific notation because it cannot be meaningfully written out in full. The universe is populated primarily by the remnants of dead stars, white dwarfs cooling into black dwarfs, neutron stars and black holes, all drifting through an expanding, darkening void. There is no starlight. There are no nuclear reactions producing warmth. The universe has become, in the most profound sense, dead in the way that we associate with warmth and light and life. But even this is not the end, because even in the silent dark of the Degenerate Era, strange things are happening on timescales that defy intuition. Protons, the fundamental particles that make up the nuclei of atom, the building blocks of all matter, may not be eternal. A theoretical concept called proton decay, which has never been directly observed but is predicted by certain grand unified theories of physics, suggests that given enough time, even a proton will eventually break down into lighter particles. The timescale for this is mind-bending, approximately 10 to the power of 34 years. For comparison, The current age of the universe is 10 to the power of 10 years. Proton decay would occur on a timescale so immense that the entire history of Stelliferous era, all 100 trillion years of stars burning and dying, would be to that timescale what the first nanosecond of the Big Bang is to the current age of the universe. If proton decay is real, it means that even the cold, black dwarf and neutron stars of the far future will eventually dissolve. The very matter that makes them up will decay into radiation and lighter particles over unimaginably vast stretches of time. The solid remnants of dead stars will simply evaporate, particle by particle, until nothing remains but a diffuse cloud of electrons, positrons, neutrons, and photons. A universe of ghost particles drifting through infinite darkness. The black holes remains longest of all. After all, other matter has decayed after the last black dwarf has evaporated. Black holes will still be there, patient, massive, slowly doing something that the physicist Stephen Hawking predicted in the 1970s and that bears his name. Hawking radiation is one of the most remarkable theoretical discoveries in the history of physics. Hawking showed that black holes are not completely black, that due to quantum effects at the event horizon, they will very slowly emit radiation, losing mass in the process. Over an unimaginably vast period of time, this process will cause even the largest black hole to eventually evaporate completely, radiating its entire mass away into the universe as a whisper of thermal radiation. The time scale for a supermassive black hole at the center of a galaxy to evaporate through Hawking radiation is approximately 10 to the power of 100 years. A number so large it is called a gogol, a 1 followed by 100 zeros. When the last black hole evaporates, in that inconceivable remote future, the universe will enter what cosmologists call the dark era. There is no matter. There are no stars, no planets, no black holes, no white dwarfs, no neutron stars. There is only radiation, ever thinning, ever cooling, spreading across an ever expanding universe. The temperature of the universe already close to absolute zero. Never quite reaching it, but getting closer with every passing eon. The universe will be, for all functional purposes, dead. Not in a dramatic, explosive sense, but in the most quiet and complete way imaginable. A vast, dark, cold, structureless expanse of nearly nothing, the last photons traveling through it so spread out and so low in energy that they barely qualify as a light. This scenario, the long, slow heat death of the universe, is the most widely accepted prediction for the ultimate fate of the cosmos, based on the current cosmological models and the observed behavior of dark energy. The mysterious force that is causing the universe to expand at an accelerating rate. As the universe expands, matter and energy become more and more diluted. The average temperature drops towards absolute zero. Entropy, a measure of disorder and the dispersal of energy, increases relentlessly as the second law of thermodynamics demands it must. And eventually, given enough time, entropy reaches its maximum possible value. There are no gradient, no more differences in the temperature or pressure that could power any kind of process, physical, chemical, or biological. The universe reaches a state of perfect eternal equilibrium and nothing ever happens again. This is a concept called the heat death of the universe. and it was first proposed by physicists in the 19th century. Even then, long before cosmology had developed the tools to estimate the actual timescales involved, the idea was recognized as deeply profounding disturbing. The philosopher Bertrand Russell wrote about it in the early 20th century with barely concealed anguish, describing the universe as a place where all human achievement and aspiration would eventually be buried beneath the ruins of a dying cosmos. The heat death scenario means that the story of the universe has, in the most fundamental sense, a plot. And the plot ends, not with a bang, not with a rebirth, but with a silence so complete and so final that even the concept of silence requires something to be silent, and there is nothing. But here is where story becomes genuinely strange, because our universe may not be the only story being told. The concept of the multiverse, the idea that universe is one of potentially infinite universe existing alongside each other, each with its own laws of physics, its own constants, its own history, is not strictly speaking confirmed, but it emerges naturally from several different and independent branches of theoretical physicists. Inflationary cosmology, which describes the rapid expansion of the early universe, predicts conditions under which new universe could continuously bubble into existence, each spawning from a quantum fluctuation in the fabric of space-time. String theory and its variants suggest a vast landscape of possible physics configurations, each corresponding to a different universe with different fundamental constants. The many-world interpretation of quantum mechanics implies a universe that is constantly branching, every quantum event spawning in new realities. If any of the version of the multiverse is correct, then the death of the last star in our universe and the subsequent extinction of all structure and energy is not the end of everything. It is simply the end of our particular story. Somewhere in the infinite form of possible realities, other universes may be young and star-rich, teeming with light and heat and the raw materials for complexity. Others may have different laws of physics entirely, supporting structures and processes that have no analog in our universe. The death of our cosmos in this view is like the extinguishing of one candle in a room that contains an infinite number of candles, most of which we can never see, never reach, and never communicate with. There is also the possibility, remote, speculative, but not physically forbidden, that intelligence life itself might find a way to survive. This idea has been explored seriously by physicists and cosmologists, and it raises questions that are philosophical as they are scientific. Freeman Dyson, one of the 20th century's most creative theoretical physicists, published a paper in 1979 exploring whether an advanced civilization could survive the long-term cooling of the universe indefinitely. His conclusion, based on a clever argument about the relationship between information processing and energy consumption, was surprisingly optimistic. As the universe cools and energy becomes scarce, a civilization could in principle slow down its information processing, think more slowly, essentially consuming less and less energy while still maintaining the same amount of thought over infinite time. In Dyson's universe, intelligence does not need to die just because stars do. Later work by the physicist Frank Tipler pushed this idea even further with his omega point theory, a controversial proposal suggesting that as the universe approaches its final state, the gravitational collapse of a closed universe could drive information processing into infinite density, creating a kind of cosmic consequences at the very end of time. Typler's ideas are not widely accepted by mainstream cosmology, and the observational evidence that the universe is not closed but instead accelerating towards eternal expansion makes the specific details of his proposal difficult to maintain. But the spirit of the question he was asking, can intelligence outlast the stars, remains one of the most intriguing and emotional resonant questions that physics and philosophy share. And there is something else worth sitting with. Something more immediate and more personal than the abstract timescales of cosmic death. Consider what it means that we live now, right now, in the very early universe, in the stelliferous era, in the epoch of stars. The universe is approximately 13.8 billion years old. The stelliferous era will last roughly 100 trillion years. That means we are currently living at approximately 0.01% mark of the age of stars. We are extraordinarily, almost incomprehensibly early. If the stelliferous era were a single calendar year, humanity's entire history, every war, every civilization, every work of art and science and love would fit into the first few milliseconds of January 1st. We are not living in the middle of cosmic history. We are not even living near the beginning. We are living before the beginning has properly started. This has strange implications that some cosmologists find genuinely unsettling. If the universe will last for 100 trillion years and intelligent life is possible throughout much of that time, then statistically we would expect more intelligent observers in the universe history to arise near the middle or toward the end of stelliferous era, not at the very start. Some thinkers have used this observation, known in some formulations as the doomsday argument, to suggest unsettling conclusions about the future of intelligent life. Others have proposed that early universe life may simply be rare by nature, and the conditions enabling life as we know it, rocky planets, liquid water, stable stars, are more common now than they will be in the future. On the other hand, some researchers have argued that planets in the far future, orbiting stable red dwarf stars for trillions of years, might have even more time to develop life and intelligence than we have had. The universe's story in this view may only just be beginning in terms of biological richness. There is a concept in astrophysics called the cosmic habitable age. The idea that the universe has a window of time during which conditions are favorable for life, and that we exist within but perhaps not at the center of that window. Red dwarf stars, those dim, patient final lights, are the most common stars in the galaxy and the longest lived. A planet orbiting a red dwarf in the habitable zone, close enough to be warm, far enough to have liquid, could in principle support life for trillions of years. Long after our sun has died and the earth has been swallowed, long after every sun-like star in the galaxy has burned out, these dim red embers will still be quietly shining, still warming their planets, still providing the energy gradients that life requires. The universe in its middle age, billions of years from now, might be more biologically rich than it is today, not less. But all of this is contingent on a universe that maintains the physical conditions for complexity: matter, energy, temperature gradients, chemistry. And the second law of thermodynamics, that most merciless of physical laws, guarantees that these conditions will not last. Every process that happens in the universe increases entropy. Every fire that burns, every star that shines, every thought that is thought, all of it generates entropy. all of it nudged the universe one infinitely small step closer to the final equilibrium. The universe's capacity for complexity, for structure, for life is not infinite. It is vast, unimaginably vast, but it is finite. And a finite capacity given infinite time is always eventually exhausted. This is perhaps the most philosophically challenging implications of cosmology. We can accept the death of individual people and with effort the death of species, and with more effort still the death of planets and solar system. But the death of the universe itself, the extinguishing of every possibility of every experience, is a different kind of loss. It is not a loss that any particular being will witness. It is not a loss that will cause anyone to grieve because there will be no one left to grieve. It is simply the end of the story, written in the equations of physics and sealed into reality from the very first moment of the Big Bang. And yet, the story between now and that ending is extraordinary. Consider what has already happened. The Big Bang created matter and energy. Gravity assembled that matter into stars. Stars fused hydrogen into heavier elements, carbon, oxygen, nitrogen, iron, and scattered those elements across the galaxy in explosive deaths. The next generation of stars incorporated those elements into new solar system. On at least one of those solar systems, on at least one rocky planet, chemistry somehow impossibly became biology. Molecules organized themselves into cells, cells organized themselves into organisms, organisms organized themselves into ecosystems. And after billions of years of this extraordinary experiment in increasingly complexity, one species of organism developed the capacity to understand nuclear fusion, to measure the age of the universe, and to write down the date on which the last star will die. We are the universe knowing itself. We are the 13.8 billion year product of stellar nuclear reactions becoming aware of their own eventual ending. There is something more devastating and magnificent about that. The light from the stars that shine tonight has been traveling for years, centuries, millennia to reach your eyes. The atoms in your body were forged in the nuclear furnaces of that stars that died before the earth existed. You are, in the most literal physical sense, made of starlight. And one day the starlight will end. The last nuclear reaction in the last red dwarf will fail. The last photon will be emitted. The universe will grow dark and cold and still. But before that, for the next 100 trillion years, give or take, there will be stars. There will be light and warmth and the energy gradients that make complexity possible. There will perhaps be life on worlds we cannot yet see, under suns we do not yet know, in forms we cannot yet imagine. The universe, for all its eventual fate, is for now richly, extravagantly, almost recklessly alive with possibility. The question that death of the last star ultimately leaves us with is not really a scientific question at all. It is a human question. It is the question that has driven philosophy and religion and art since the first human being looked up at the night sky and felt simultaneously enormous and impossibly small. The stars will die. The universe will grow dark. Every trace of everything that has ever mattered to anyone will eventually be erased by entropy and expansion and the patient arithmetic of thermodynamics. Given all of that, given the absolute certainty of this cosmic ending, what does it mean to be here now? What does it mean to burn briefly, brilliantly in the middle of this darkness? The last star will die in approximately 100 trillion years. The universe in its current form has been burning for 13.8 billion years. And right now, at this precise and unrepeatable moment, you are sitting under a sky full of lights. Every one of them a nuclear furnace. Every one of them temporary. Every one of them for tonight at least still shining. Perhaps the most profound thing that the death of the last star teaches us is not about endings at all. Perhaps it teaches us about the staggering, almost accidental preciseness of now. This moment, this era, this brief and improbable window of time when the universe is still young and warm enough and alive enough for a mind to look upward and ask questions about it. The universe does not need us to understand it. It was old before we arrived and will continue long after we are gone. But we are here. We are looking. We are asking. And perhaps that, the act of asking, the refusal to look away, the insistence on understanding even the face of an indifferent cosmos, is its own kind of light. Small, yes. Temporary, certainly. But real and for now, burning.